Imagine a world where China controls the very brains of our technology. From your smartphone to advanced AI, for decades ASML has held the keys to the most advanced chip manufacturing with their EUV machines. But what if China is on the verge of cracking that code, threatening to upend global power dynamics and achieve true chip independence? To understand the magnitude of this potential geopolitical pivot, we must first descend into the microscopic cathedral of the machine itself, a device so complex that it has been rightfully termed the most sophisticated object ever constructed by human hands, the Extreme Ultraviolet Lithography System, or EUV, which stands not merely as a tool of industry but as a solitary peak, an impossible mountain of engineering that currently separates the masters of the Silicon Age from those who merely inhabit it. We begin our journey in the sterile, amber-lit silence of a semiconductor fabrication plant, a clean room environment where the air is filtered to a purity that makes a hospital operating theater look like a dust storm, and where the temperature is controlled to within a few thousandths of a degree to prevent the thermal expansion of materials that could ruin the nanoscopic architecture of the future. Before we move on, if you like learning this way, you can quietly hit subscribe so you don't lose this channel later. Here, resting on a seismic isolation block that separates it from the vibrations of the Earth itself, sits the machine, a bus-sized behemoth weighing 180 tons, a convergence of physics, chemistry, and optics that operates at the very edge of what is theoretically possible. The heart of this machine is a violent, paradoxical engine of light creation, a process that begins not with a bulb or a diode, but with a falling droplet of molten tin, a metallic tear no wider than a human hair, plummeting through a vacuum chamber with perfect predictability. We must slow our perception of time to the nanosecond to appreciate the violence required to birth the light that carves our digital reality, for as this tin droplet falls, it is tracked by sensors that relay its position to a high-power carbon dioxide drive laser, a weapon of focused energy that fires a pre-pulse to flatten the droplet into a pancake shape, increasing its surface area for the main event. Microseconds later, the main pulse arrives, a hammer of pure photonic force that strikes the flattened tin with such intensity that the metal is instantly vaporized, stripped of its electrons, and transformed into a plasma. The fourth state of matter, burning at temperatures reaching hundreds of thousands of degrees Celsius, hotter than the surface of the sun. It is from this superheated ionized frenzy that the specific wavelength of light we seek is born, 13.5 nanometers, the extreme ultraviolet, a wavelength so short, so fragile, that it is absorbed by virtually everything in the known universe, including air itself, which is why the entire operation must occur within a high-grade vacuum, a void where nothing exists to steal the precious photons before they can do their work. This light, this ghost of the electromagnetic spectrum, flows outward from the plasma in all directions, but capturing it requires a feat of optical engineering that defies conventional logic, for at this wavelength, glass lenses are useless, absorbing the light rather than refracting it, and so the machine must rely entirely on mirrors. Yet these are not mirrors as we understand them in the bathroom or the telescope, but Bragg reflectors, marvels of material science constructed from alternating layers of molybdenum and silicon, each layer only a few nanometers thick, stacked with atomic precision to create a resonant structure that reflects the EUV light through constructive interference. The flatness of these mirrors is a statistic that breaks the human imagination, for if one of these mirrors was scaled up to the size of the country of Germany, the highest mountain and the deepest valley on its surface would vary by less than a single millimeter, a level of smoothness that approaches the theoretical limit of physical perfection. This light, gathered and focused by a series of these impossible mirrors, is then projected onto a silicon wafer coated with light-sensitive chemicals, etching patterns so small that they are measured in atoms, creating the transistors that act as the neurons of our artificial intelligence, the logic gates of our supercomputers, and the memory of our collective history. This is the Dutch secret, the fortress of intellectual property and tacit knowledge that ASML has built in Veldhoven, a monopoly not born of ruthless business tactics alone, but of the sheer, vertiginous difficulty of the task, a complexity that acts as a natural barrier to entry for any nation or corporation daring to replicate it. It is crucial to understand that an EUV machine is not simply a product assembled in a factory, but the culmination of a global supply chain that functions like a singular, distributed organism involving over 5,000 specialized suppliers, each a master of a specific domain. Zeiss in Germany for the optics that effectively defy the Heisenberg uncertainty principle, Trumpf for the lasers that deliver the power of a lightning bolt with the precision of a scalpel, and Cyma in San Diego for the light source technology, creating a web of interdependencies that is as fragile as it is powerful. The integration of these components requires a symphony of software and hardware, where sensors adjust the position of the wafer and the reticle thousands of times per second, compensating for distortions caused by the heating of the mirrors, the vibration of the floor, and even the minuscule changes in atmospheric pressure outside the vacuum chamber. To attempt to build such a machine from scratch is to attempt to replicate the entire industrial history of the Western world's high-tech sector. For the knowledge required is not written down in a manual that can be stolen or copied. It lives in the muscle memory of the engineers who have spent decades polishing lenses, in the intuition of the physicists who have spent careers stabilizing plasma, and in the proprietary algorithms that stitch the chaos of quantum mechanics into the orderly rows of a microchip. The cost of entry is astronomical, not just in terms of the billions of dollars required for research and development, but in the cost of failure, the years of trial and error, the explosions of tin that coat delicate optics in debris, the lasers that misfire, the vacuum seals that leak, and the sheer relentless physics that seem to conspire against the creation of structure at this scale. ASML spent over 2 decades and poured billions into the development of EUV before a single commercially viable machine rolled off the line, a testament to the impossible mountain that any competitor, including China, must climb without the aid of the maps, the ropes, or the guides that the incumbents have spent a generation acquiring. This is the baseline reality, the starting line of the race, a technology that sits at the pinnacle of human achievement, a machine that converts electricity into computation through a process that borders on magic, protected by a moat of complexity so wide and so deep that crossing it requires not just money but a fundamental reimagining of national will and scientific capability. As we gaze into the heart of this machine, watching the strobe light flicker of the plasma 50,000 times a second, we realize that we are looking at the bottleneck of the 21st century, the single point of failure and the single point of control for the digital destiny of the species, and it is here, at the foot of this impossible mountain, that the story of China's ambition begins, a story not of copying a gadget, but of attempting to conquer the laws of physics in isolation. If the interior of the ASML machine is a cathedral of established dogma, a sanctuary of physics tamed by decades of slow, methodical cooperation among the Western allies, then the landscape of China's answering ambition is a sprawling, frenetic construction site, a place where the cement of national will is being poured into the foundations of a new technological reality at a pace that suggests not just industrial policy, but existential survival. To understand Project EUV in its Chinese context, one must first sit with the silence that descends upon a room of policymakers in Beijing when the true vulnerability of the state is laid bare on a spreadsheet, a moment of reckoning where the terrifying asymmetry of the modern world becomes undeniable, that despite being the factory of the world, despite assembling the iPhones and the laptops and the servers that run the global economy, the actual thinking matter within those devices, the silicon brains are imported, arriving in crates that could be stopped at any moment by a signature on a piece of paper in Washington or The Hague. This realization, crystallized in the Made in China 2025 initiative, is not merely an economic plan, but a visceral reaction to the sensation of a hand tightening around the nation's digital carotid artery, a recognition that importing $300 billion worth of semiconductors annually, more than the cost of all the oil the country consumes, is a strategic liability so profound it borders on a national emergency. Consequently, the mobilization we are witnessing is less like a corporate R&D cycle and more like the Manhattan Project or the Apollo program, a whole-of-nation system, or Juguotiti, where the distinction between the state, the academy, and the private sector dissolves into a singular directed vector of force. We must visualize the sheer hydraulic pressure of capital being unleashed through the Big Fund, the National Integrated Circuit Industry Investment Fund, which does not simply write checks but floods the ecosystem with liquidity, creating a high-stakes environment where tens of billions of dollars circulate through the industrial parks of Shanghai, Wuhan, and Shenzhen, seeking purchase in any laboratory promising a breakthrough. In these laboratories, the atmosphere is thick with a specific kind of tension, a mixture of patriotic fervor and the crushing weight of impossible expectations, where teams of engineers at entities like Shanghai Microelectronics Equipment, SMEE, and the Changchun Institute of Optics, Fine Mechanics and Physics are attempting to compress 40 years of global lithography evolution into a single decade. Imagine the scene inside one of these domestic research facilities. It is late. The hum of the H5AAC systems provides a relentless drone, and a team of young physicists, many of whom were educated in the very Western universities they are now trying to outpace, stare at the telemetry data of a prototype light source that is failing to stabilize. They are not merely trying to reverse engineer a machine, they are trying to reconstruct a missing civilization of knowledge, for while they can buy a used DUV machine and dismantle it to study the lens curvature or the stage mechanics, the EUV remains a black box, a ghost that cannot be touched. The challenge they face is getting the big fund money to transmute into ultraviolet photons, a chaotic alchemy where the funding buys the best vacuum chambers money can buy and the purest raw materials, yet the fundamental physics remains stubborn, refusing to yield to budget surpluses alone. We see them experimenting with alternative pathways, divergent ideas that the West may have discarded or overlooked, such as the steady-state microbunching, SSMB, project being explored at Tsinghua University, a concept that abandons the violent tin-droplet plasma model of ASML in favor of a particle accelerator ring, a massive synchrotron tailored to generate continuous high-power EUV light. Visualize a facility not the size of a bus, but the size of a football stadium, a ring of magnets guiding electron beams to dance in a precise undulation, releasing light as they turn, a desperate and brilliant attempt to bypass the patent walls of Cymer and Zeiss by simply building a light source so large and so powerful that it serves multiple lithography scanners simultaneously, a factory built around a central glowing heart. But this ambition is haunted by ghosts, specifically the specter of past failures that linger in the collective memory of the Chinese scientific community, most notably the Hanxin scandal of the early 2000s, where a researcher claimed to have invented a domestic digital signal processor that rivaled Western chips, securing massive government funding and accolades, only for it to be revealed that he had simply purchased Motorola chips and hired a migrant worker to sand off the logos with sandpaper. The memory of that sandpaper, the gritty sound of fraud scratching away the truth, creates a paranoid friction in the current drive, a demand for verification, for results that are tangible, leading to a ruthless pressure on the scientists of today to show progress, to demonstrate that this time the silicon is real. This pressure creates a crucible where the engineers are working 996 schedules, 9 a.m. to 9 p.m., 6 days a week and often far beyond, sleeping on cots in the hallways of the labs, driven by a narrative that frames their work as the modern equivalent of the two bombs, one satellite era, when isolated China developed its nuclear deterrent and space capabilities in the 1960s. Yet, lithography is arguably harder than a nuclear bomb. A bomb only has to work once, and its violence is forgiving of small imperfections, whereas a lithography machine must work perfectly, billions of times in a row, with a precision that tolerates no error, no debris, no variation. As the state pours resources into the little giants, specialized startups focused on the thousands of unsexy subcomponents like photoresist chemicals, electrostatic chucks, and pellicles, we see a map of the supply chain being redrawn, with the government explicitly targeting the choke points where foreign monopolies exist. It is a grind, a slow, attrition-based warfare against the complexity of the supply chain, where for every step forward, like achieving 28-nanometer resolution with domestic equipment, the horizon of 3-nanometer EUV retreats further into the distance, moving as fast as the competitors run. The walls of these Chinese labs are not just containing high-pressure gases, they are containing the pressure of a rising superpower that has realized it built its house on land owned by a rival and is now frantically trying to pour a new foundation before the lease expires. We must look closely at the eyes of the project leads, the chief commanders of these scientific detachments, who know that the sheer volume of money, tens of billions in the latest tranche of the big fund, cannot buy the tacit knowledge that lives in the fingers of a German lens polisher or a San Diego plasma physicist, and so they must grow that knowledge organically, painfully, through a process of trial and catastrophic error, burning through prototypes, melting mirrors, and crashing wafer stages, all while the clock ticks down toward a decoupling that seems inevitable. This is the texture of China's ambition, It is not a sleek, inevitable march to victory, but a messy, high-stakes, sweat-drenched struggle in the mud of material science, a gamble that the brute force of a command economy can eventually simulate the delicate symphony of a global free market, a bet that if you throw enough money, talent, and time at the laws of physics, eventually the light will shine. To cross the threshold from ambition to reality, the Chinese engineering apparatus must now confront the physical manifestation of the impossible mountain, a series of technical paradoxes that do not merely require innovation but demand the violation of what feels like intuitive Newtonian physics, beginning with the most excruciatingly precise object in the entire assembly, the perfect mirror, or more accurately, the Bragg reflector system. Unlike the lenses of the deep ultraviolet (DUV) era, which were crafted from fused silica and calcium fluoride to refract light through a transparent medium, the extreme ultraviolet photons at 13.5 nanometers act as a universal dissolvent of optical clarity absorbed by every known transparent material, forcing the engineers to abandon the concept of a lens entirely and rely on reflection alone. Yet, this is not the reflection of a silvered bathroom mirror, which creates a ghost image and absorbs too much energy, but a reflection born of quantum interference, requiring a mirror coating constructed from alternating strata of molybdenum and silicon, a bilayer stack where each layer is exactly 3.4 nanometers thick, stacked 40 to 50 times high, to create a resonant structure that tricks the light into bouncing back. Before we move on, if you like learning this way, you can quietly hit subscribe so you don't lose this channel later. The challenge facing the researchers at the Changchun Institute is that the interface between these two materials must be sharp to the atomic level. If the atoms of silicon drift into the molybdenum, forming silicide, the reflectivity drops and the machine goes dark. And this deposition must be uniform across a curved surface that is nearly half a meter wide, a geometric nightmare where the coating thickness cannot vary by more than the width of a single atom from the center to the edge, or the wavefront of the light will distort, ruining the focus. The refront of the light will distort, ruining the focus. Even with this perfection, the tragedy of EUV optics is the photon budget, a relentless economic depression of light where even the most perfect Bragg mirror reflects only about 70% of the incident photons, meaning that 30% of the energy is lost, absorbed as heat at every single bounce. Since the optical path inside the scanner requires perhaps a dozen such mirrors to shape and shrink the image, the light intensity decays exponentially, following the ruthless mathematics of compound loss, so that by the time the beam reaches the silicon wafer, only 1 or 2% of the original light generated by the source remains, a scarcity that turns every photon into a precious commodity that cannot be wasted. This necessitates a light source of blinding, hellish initial intensity to compensate for the losses, bringing us back to the tin-droplet plasma, which China must not only generate but control with a stability that borders on the preternatural, for the process is not a steady beam, but a strobe light flickering 50,000 times per second, and each flicker is a coordinated assassination of a falling droplet. We must zoom in on the specific kinetics of this dual pulse interaction, a sequence that the Chinese teams are struggling to master. First, a low-energy pre-pulse laser strikes the spherical tin droplet, not to vaporize it, but to shock it, causing it to expand and flatten into a pristine disc-shaped pancake of liquid metal, a shape that presents a larger target and optimized density profile for the second act. Microseconds later, the main drive laser, a carbon dioxide laser amplifier system of immense power, slams into this pancake, dumping kilowatts of energy into the metal in nanoseconds, stripping the electrons from their nuclei and creating the high-temperature plasma that emits the EUV light. The engineering hurdle here is not just the laser power, but the debris mitigation, for this explosion is a dirty bomb, spraying high-energy tin ions, neutral atoms and shrapnel in all directions, a corrosive mist that, if left unchecked, would coat the multi-million-dollar collector mirror in a layer of tin within minutes, rendering it useless. To combat this, the machine must employ a dynamic shield of hydrogen gas, a flowing curtain of buffer gas that intercepts the flying tin debris, reacting with it to form stananae, SNH4, a gas that can be pumped away, while simultaneously slowing down the heavy ions before they can sputter the mirror coating. However, this hydrogen gas also absorbs some of the precious EUV light, creating a maddening optimization loop where the engineers must inject enough gas to save the mirrors, but not so much that they snuff out the light, a balance that requires fluid dynamics modeling of a complexity that rivals planetary weather simulations. Furthermore, the entire optical train must be contained in a vacuum vessel that is cleaner than the void of space for even a few molecules of hydrocarbons. Vapor from a fingerprint, outgassing from a wire insulation, or oil from a pump will be cracked by the high-energy photons, leaving a carbon residue on the mirrors that permanently darkens them, a phenomenon known as carbonization, which necessitates a secondary cleaning system using hydrogen radicals to scrub the mirrors atom by atom without breaking the vacuum. Beyond the light source and the optics, the Chinese engineers face the stage challenge, the electromechanical system that holds and moves the silicon wafer and the pattern reticle, which must dance in opposite directions with a synchronization that defies belief. The reticle stage moves at 4 times the speed of the wafer stage to account for the demagnification of the lens, accelerating at several times the force of gravity, faster than a drag racer, yet it must know its position to within a few nanometers at all times. This is not achieved with gears or ball screws, which have friction and backlash, but with magnetic levitation, maglev, linear motors floating in a vacuum, guided by laser interferometers that measure distance by counting the peaks and troughs of light waves, a feedback loop where the sensors, the actuators, and the control algorithms must communicate in microseconds to correct for the tiniest vibrations, even the vibration caused by the cooling water rushing through the pipes of the machine itself. The little giants and the state-owned enterprises are thus not building a single machine, but attempting to orchestrate a symphony of thousands of subcomponents. Ultra-low expansion glass ceramics that do not change size when heated, electrostatic clamps that hold the wafer flat without touching its front surface, and spectral purity filters that strip away the infrared heat from the laser while letting the EUV light pass, each of which constitutes a PhD-level physics problem in its own right, and all of which must work together with 99.99% reliability, for in a semiconductor fab, a machine that is down for maintenance is a machine that is burning money, and a supply chain that creates a machine that works only most of the time is a supply chain. This is the granular texture of the barrier China faces. It is not a wall of patterns, but a wall of integrated performance, where the mastery of one variable, like plasma temperature, is useless without the mastery of the adjacent variable, like mirror cooling, creating a lock that requires 10,000 keys to turn simultaneously, a feat that ASML achieved through 40 years of stumbling, learning, and collaborating, and which China is now attempting to brute force through a compressed timeline of intense, breathless, and solitary engineering. While the engineers in Shanghai and Changchun wrestle with the immutable laws of physics, a different kind of war is being waged across the oceans, a conflict fought not with lasers and plasma, but with administrative codes, export licenses, and the quiet, suffocating violence of the entity list, a geopolitical chessboard where the United States and its allies attempt to construct a digital iron curtain around the People's Republic. To understand the visceral impact of these sanctions, we must look beyond the dry text of the October 7, 2022 export controls issued by the Bureau of Industry and Security, and instead visualize the immediate kinetic freezing of a global circulatory system, a moment where the intricate web of commerce that binds Silicon Valley to Shenzhen was severed with the stroke of a pen. Imagine the scene at a loading dock in the Netherlands or Japan, where crates containing critical subsystems, perhaps a set of cryopumps or a specialized canister of photoresist, are suddenly flagged, their barcodes turning red on a logistics terminal, effectively stranding the hardware in a legal limbo that is as impenetrable as a physical blockade. This is the Foreign Direct Product Rule in action, a legal extraterritorial tentacle that allows Washington to dictate the destiny of any item made anywhere in the world, provided it contains even a trace of American technology or software, a stipulation that effectively turns every piece of advanced semiconductor equipment into a potential vehicle of U.S. foreign policy. For the Chinese foundries like SMIC, Semiconductor Manufacturing International Corporation, this is not merely a supply chain hiccup, it is an asphyxiation event, a realization that the very air they breathe, the electronic design automation, EDA, software from Cadence or Synopsys used to design the chips, the metrology tools from KLA used to measure them, and the lithography scanners from ASML used to print them, is controlled by ASML, used to print them, is controlled by a rival power that has decided to turn off the tap. The atmosphere inside the Chinese tech sector shifts from competitive urgency to existential dread as the kill switch is theoretically pulled, forcing a frantic inventory of every single screw, gasket and line of code to determine what can be replaced by a domestic alternative and what is a choke point that could halt production entirely. Simultaneously, this geopolitical freezing creates a profound human crisis, a talent war that rips through the academic and industrial communities, transforming the movement of scientists into a matter of national security. We must consider the psychological toll on the thousands of Chinese-born, Western-educated researchers who have spent decades traversing the Pacific, building bridges of knowledge between Stanford, MIT, and Tsinghua, who now find themselves walking through a minefield of suspicion. The China Initiative and its successors, while ostensibly designed to counter espionage, cast a long shadow, creating a chilling effect where a collaboration email or a conference presentation can be scrutinized as a potential act of treason or IP theft. This leads to a painful decoupling of human capital, where top-tier talent faces a dilemma: remain in the West and face a glass ceiling of security clearances and suspicion, or return to China to join the Project EUV effort, bringing their knowledge back to the motherland but cutting themselves off from the global mainstream of research. The narrative of espionage versus innovation thus becomes the central tension of the era, fueled by headlines of data breaches at ASML, where an employee is accused of misappropriating proprietary information, yet we must understand the nuance that stealing the blueprints of an EUV machine is not the same as possessing the machine. You can steal the terabytes of schematics for a Bragg mirror, you can download the source code for the wafer stage control, but you cannot steal the tacit knowledge. The intuition of the master technician who knows exactly how much torque to apply to a mounting bolt to prevent thermal drift, or the specific acoustic signature of a pump that is about to fail. This knowledge cannot be hacked. It must be lived, experienced, and accrued through failure, meaning that even with the stolen plans, China is forced to rederive the physics, to rewalk the path, albeit with a stolen map in their pocket. Sanctions, paradoxically, may have achieved the exact opposite of their long-term intent. Instead of permanently crippling China's chip capabilities, they have removed the crutch of easy access to Western tech, forcing the Chinese system to abandon the path of least resistance, buying from ASML, and commit fully to the harder, slower, but ultimately sovereign path of indigenous innovation. It is a Sputnik moment in slow motion. A realization in Beijing that reliance on the global market is a strategic vulnerability that can no longer be tolerated, leading to a doubling down of the Zhuguo-Tiji system, where the state effectively guarantees the market for domestic equipment makers, telling foundries that they must use Chinese machines, even if they are inferior, even if the yield is low, simply to keep the ecosystem alive and learning. We see the formation of a red supply chain, a parallel universe of technology standards and protocols completely divorced from the West, a bifurcation of the digital world where, in the future, a chip made in Shanghai might rely on fundamentally different architectures, materials, and manufacturing philosophies than a chip made in Arizona or Taiwan. The geopolitical chessboard is thus not just about blocking a machine. It is about the fracturing of the globalization of science itself, a return to a Cold War style of compartmentalized progress, where two great powers race toward the same finish line. Atomic-scale computing, running on separate tracks, separated by a wall of silence, mistrust, and export controls, with the rest of the world forced to choose which operating system they wish to inhabit. The stakes of this shadow war are absolute, for whoever controls the lithography controls the compute, and whoever controls the compute controls the future of artificial intelligence, economic modeling, and military supremacy, making the quiet hum of the cleanroom fan filter unit the sound of the most consequential front line in modern history. Let us cast our minds forward, projecting the current vector of industrial will and capital accumulation into the haze of the 2030s, to visualize the moment when the impossible mountain is finally summited, a hypothetical yet increasingly plausible Tuesday morning in a fabrication plant on the outskirts of Shanghai, where the first fully indigenous, commercially viable extreme ultraviolet lithography scanner completes its acceptance test. This is not merely a technical milestone like the breaking of the sound barrier or the landing on the moon, but a geostrategic singularity, a point in time where the tectonic plates of the global order shift with a grinding subsonic resonance that is felt in the boardrooms of Silicon Valley, the ministries of Taipei, and the intelligence agencies of Washington. Imagine the scene on the cleanroom floor. the yield monitors, which for years flickered with the heartbreaking statistics of failure. Wafer after wafer rejected due to stochastic defects, overlay errors, or tin debris contamination, suddenly stabilize at a commercial grade of 85%, signaling that the red supply chain has successfully closed the loop. If you reach the end, thank you for your time. If you'd like to support this style, a like and a subscribe makes a bigger difference than you think. In this future scenario, the monopoly of ASML is not necessarily broken but bypassed, rendered less absolute as China begins to flood the market, not just with the legacy chips that run washing machines and cars, which it likely already dominates by this time, but with the high-performance logic gates that define the frontier of artificial intelligence, high-frequency trading, and autonomous warfare. The immediate implication is the vaporization of the silicon shield, the long-held theory that the world's reliance on Taiwan for advanced semiconductors serves as a guarantee of its security. If China can print its own 5nm and 3nm chips at scale, the strategic calculus of a blockade or an invasion transforms from a threat of mutual economic suicide into a manageable cost of doing business, fundamentally altering the deterrence architecture of the Indo-Pacific. Economically, the arrival of a Chinese EUV machine introduces a deflationary shock to the semiconductor industry, similar to what Chinese manufacturing did to solar panels and steel. Stripped of the need to pay the premium prices commanded by the Western monopoly and backed by state subsidies that prioritize market share over quarterly profits, Chinese foundries could drive the cost of compute down to near marginal levels, democratizing access to supercomputing power while simultaneously eroding the profit margins that Western firms rely on to fund their next generation of R&D. This creates a bifurcated digital reality, a splinter net of hardware where the world is divided into two distinct technological spheres, one running on the trusted, verifiable, but expensive silicon of the Western Alliance, and another running on the ubiquitous, subsidized, and opaque silicon of the Chinese ecosystem, with nations in the global south forced to choose between the two based on price and political alignment. However, the most profound implications are likely invisible to the consumer, residing instead in the dark, silent racks of military server farms and the guidance systems of hypersonic platforms, for chip independence is the prerequisite for military AI supremacy. Without the ability to manufacture the latest GPUs and TPUs domestically, a modern military is effectively capped, unable to train the massive neural networks required for autonomous drone swarms, real-time battlefield analysis, and cryptographic decryption. A functional domestic EUV capability removes this cap, allowing the People's Liberation Army to decouple its modernization capabilities from the whims of US export controls, unleashing a torrent of computational power that can be embedded into everything from missile seekers to orbital surveillance satellites, creating a kill web that operates at the speed of light. Yet, as we stare into this potential future, we must also acknowledge the long road ahead, the sobering realization that the lithography scanner, for all its complexity, is only one organ in the body of the semiconductor ecosystem, and possessing it does not grant instant omnipotence. Even with a working EUV machine, the Chinese engineers face the Herculean task of mastering the rest of the iceberg, the electronic design automation, EDA, software, currently dominated by US firms like Synopsys and Cadence, which constitutes the complex architectural blueprints without which the machine has nothing to print. Furthermore, the industry is already shifting its gaze beyond the mere shrinking of transistors to the paradigm of advanced packaging and heterogeneous integration, where performance gains are achieved not just by making features smaller, but by stacking chips vertically in three-dimensional skyscrapers of silicon, stitching together logic, memory, and sensors into single chiplet systems using interconnects that require their own exotic forms of lithography and bonding. Thus, the summiting of the EUV mountain reveals not a plateau of victory, but simply a view of the next mountain range, a landscape where the definition of advanced is constantly retreating, forcing the pursuer to run faster just to stay in the same place. The race for chip dominance is therefore not a sprint with a finish line, but an infinite game of recursive complexity, where the prize is not a trophy, but the temporary ability to define the future of human cognition, computation, and control, a future that is being written, layer by atomic layer, in the vacuum chambers of the world's most expensive machines, spinning in the dark, waiting for the light to strike. As the dust settles on the immediate geopolitical scramble for extreme ultraviolet dominance, we must ultimately lift our gaze beyond the specific rivalry of nations and confront the terminal horizon of the technology itself. For the story of lithography does not end with the current generation of machines, nor does it end with China's potential parity. Rather, it accelerates toward a theoretical hard wall, a great filter of material physics known as the Angstrom era. Even as the current impossible mountain is being climbed, ASML is already constructing the next peak, the high-NA, high numerical aperture, EUV systems, machines of such gargantuan complexity that they require their own dedicated fabrication plants, taller and wider than any that came before, designed to capture light at wider angles to resolve features even smaller than the current 3-nanometer standard. We must visualize the exiles of the future, the engineers who are already looking past silicon entirely, acknowledging that the electron, that faithful servant of the 20th century, is becoming unruly, leaking across the nanoscopic gates of transistors via quantum tunneling, a phenomenon where the particle simply teleports through the barrier that is supposed to stop it, rendering the logic gate leaky and hot. If you made it to the finish, I really appreciate you. If you want more slow, soothing science, liking the video and subscribing keeps the next one easy to find. This physical limitation heralds the end of Moore's law as we have known it, transforming the race from a sprint for smaller features into a desperate search for new materials that can carry the baton when silicon collapses under the weight of its own miniaturization. In the deep research wings of universities and secret corporate labs, the focus shifts to exotic successes: carbon nanotubes, rolled sheets of graphene that conduct electricity with zero resistance and perfect ballistic transport, or transition metal dechalcogenides, TMDS, two-dimensional materials only 3 atoms thick that promise to maintain control over electrons even at the single nanometer scale. The China versus West narrative thus becomes a mere prologue to a much larger species, wide struggle, the battle against the granularity of the universe itself. We are approaching the point where we are manipulating matter at the scale where the position of an atom is no longer a coordinate but a probability cloud, a fuzzy reality that resists the deterministic logic of binary computation. In this ultimate view, the EUV machine, whether built in Veldhoven or Shanghai, is revealed to be one of the final tools of the top-down era of manufacturing, a brute force method of carving statues out of block, soon to be replaced, perhaps in decades or perhaps in a century, by bottom-up assembly, where we do not etch patterns into stone, but program matter to assemble itself atom by atom, mimicking the biological machinery of DNA and proteins. The quantum leap is therefore not just about a chip, but about the transition of humanity from a species that shapes bulk matter to a species that authors reality at the fundamental limit of resolution. As the strobe light of the plasma source fades into the history books, it will be remembered as the anvil upon which the digital age was truly forged, the glowing, violent, impossible bridge that carried us from the macro world of steel and oil to the silent, vibrating, infinite potential of the quantum realm, leaving us to wonder not who controls the machine, but what the machine will eventually enable us to become when the silicon finally dissolves into pure information.